So today I'm going to jump a few slides and then go into directly almost to the last slide of this chapter, which is design of a common emitter amplifier, because that is lab number 8 for this week. And so let's jump right into it. My annotations are already available in the notebook, so I'm going to go over the procedure. Okay, so this is a CE amplifier or a common emitter amplifier using a BJT and a voltage divider bias. Okay, for this, first off, what we're going to start with is the transistor that you use for lab 7 and the common emitter characteristics that you generated using sweep and go. Okay, that's what we are starting. One thing I'd like to point out right at the top is that the circuit that we used, or not, that we laid out was this. Anybody remember? Lab 7. There was no emitter resistor. Okay. There was no emitter resistor. That was the biasing circuit that we used. Though we were just simply trying to obtain the characteristics. So the device characteristics do not change, right? I just want to point out that one thing first. All right, so here we have a circuit that has 4 resistors, R1 and R2, sometimes also known as RB1 and RB2, because they are the base resistors. Okay, they form a voltage divider, and hence this biasing circuit is also known as a voltage divider bias, which is again something we'll learn later on in a couple of classes. So a job as a design engineer is to determine the values of RB1, RB2, and RE. Okay, RC, the collector resistor, is given as 4.7 kilo ohms. So in the lab, it is 4.7K. In this example, it's 1 kilo ohm. The approximate gain of this circuit is RC over RE, the ratio of the collector resistor to the emitter resistor. And the question that is asked is that the gain should be at least 2. Okay, the gain should be at least 2. So safe value for a resistor would be, I don't know, at least anywhere between 1/4 to 1/5 of the collector resistor RC. So if RC is 4.7K, which is a given for all, you can choose RE to be any value less than or equal to 2.2 kilo ohms. Okay, that would ensure that the gain of your amplifier is going to be greater than 2. Okay, V out is required to be 10 volts peak to peak. There's no mention of V in. Of course, V in will depend on the gain of your amplifier, gain of your system. Okay, so this is known as the load line analysis or load line analysis of CE design, CE amplifier. So the first thing we do is we obtain the characteristics, the output characteristics. Then you're going to plot the load line. To plot the load line, does anyone remember how to plot the load line? I hear some murmurings, but my ears are not that good. Okay, so to plot the load line, apply KVL on the output side. On the output side, you have 1 voltage, VCC. We varied VCC from 0 to 16 volts. Sorry, not 0 to 16. That was to obtain the characteristics. Here, I believe in this lab, it's in this example, it's 12 volts, but in the lab, you can choose whatever value of VCC you want. Okay. In this example, it's given as 12, but in your design, you can choose whatever you want. You can choose 10, 15, 20, 30, whatever. I think our supplies do not go beyond 30. 10 probably is 10 will not work because your V out needs to be 10. So VCC must be at least greater than 11 or 12. So Again, a safe bet for VCC would be at least greater than 15. Anyway, the equation would be VCC minus ICRC minus VCE minus IERE is equal to 0. IB, if you recall, was 10, 20, 30, 40, 50 microamps. Very, very small. So we can safely ignore it, and we can write IE is approximately equal to IC. So if IE is approximately equal to IC, then I can say my equation is VCC minus IC times RC plus RE minus VCE is equal to 0. I want to obtain the entire equation in IC and VCE because those are the characteristics we have, right? We have VCE and we had IC. Now that we have our equation, find the two endpoints of the line, find the two endpoints of the line, find the intercept of the x-axis and the y-axis. So if IC is equal to 0, which means y is 0, what's the value for x? X value VCE is equal to VCC. Here's where you decide what value you want to choose. And if VCE is 0, meaning if x is equal to 0, what is y? Y is VCC divided by RC plus RE. You all with me so far? Okay. Once you have these two values, plug them in here. And you join the 2 points. Once you join the 2 points, you have your load line. This is your load line. Once you have this load line, you pick a value for IB. We want it to be somewhere in the center of the active region. So again, we had 6 sets of data, 0, 10, 20, 30, 40, 50. Center would be around 25 or 30 microamps. Pick either one. Doesn't really matter. You're designing, right? So you choose the value for IB. In this example, because my characteristics are different, the center is around 32. So I chose 32. You can choose anywhere between, I would say, 25 to 30, right? You had plots, IC versus VCE for different values of IB. You pick one value of IB, find the intercept or the intersection right there. That's your Q point. You need to extract the values for IC and VCE from that intersection point. The coordinates of that intersection point give you these values. Okay. That's the most important. Does it make sense? You have the characteristics that you obtain in lab 7. Now you're going to apply KVL, generate an equation for the output side. Find the 2 endpoint coordinates of the load line. Find the intersect of the load line and the characteristic. Choose any value for IB. Here it's 32. Once you have the Q point, the coordinates of the Q point give you the value of VCE and IC. Okay, this is the DC operating point of your amplifier. It should be somewhere in the middle of the active region. Okay, should be somewhere in the middle of the active region. So once you have that, you can just go through these steps. These are kind of self-explanatory. You can find VB, right? From IB and IC values, you find IE. From IE values, you can find VB. Once you have VB, you know the voltage that is going into your base. If you know the voltage that's going into the base, you can calculate based on these resistors, which is the voltage divider network. So your VCC plus the two resistors in that voltage divider will give you R1 and R2. Okay. So choose IR2 at least 10 times IB. IR2 is the current that would be going in. And so that's 0.32. And then from there, you can calculate R2, which is the bottom resistor. You choose a value. Again, as I said, you choose a value for IR2. If that doesn't work out and you're not able to simulate your amplifier in LT Spice, you just play around with the settings, not settings, but you play around with the values just a little bit, not too much. If you have your values correct and your simulation works, then you're 99%, your experiment is going to work in the lab and you'll be done in 10 minutes. Okay. So spend time trying to get the simulation done. If you can get the simulation done, your circuit will work. Okay. If you are so inclined, if you all 3 members of your group can come together, you can work in the SPL before the lab, get it done. Just bring the circuit in the lab class, run the simulation, show it to me, and you're done. Okay. And those of you who are not in my class, that's up to your instructor. But again, simulation is required as preparation of this lab 8. Okay. As an engineer, this is what you'd be doing if you're designing a system. You have a goal in front of you and you're working backwards. Anywhere you don't have numbers, you make an assumption and you choose a value, as we are doing in many places, right? And so design is to find the values for R1, R2, which form the base resistance. RE can be determined simply from the gain value. So we're making an assumption there. And then, if your calculations are correct and it matches up with the device characteristics, you will end up with a working amplifier. And you'd be able to see that you apply V in sine wave and you measure V out. Most of these configurations, actually all of these CE configurations will result in an inversion of the output. That's something that I will explain when we, when we do that. But I wanted to cover this slide specifically for Lab 8. Okay, so on Wednesday we'll pick up again from where we stopped on Friday. But please make sure that you review this. All right.